everybody. So I'm Neil. There's the Gemini logo. That's our current All-Ireland cooperation looking at geothermal energy. So it's really important, this, and it's something we've worked on for a long time, and it's sort of waxed and waned a wee bit, so it's glad to see it on the rise again. So, I say I should know how to remember to use Teams. Opening jocular side, as I always do, of these sort of things, is I've been working on heat pumps for probably about 40 years nearly, and they still surprise you. You still always something to learn, something to discover. And there's a theme throughout this thing about new working fluids. I'll mention it later, but environmental concerns, not just for saving CO2, which heat pumps are very good at doing, but what they have inside them to do that is sometimes a bit of a challenge. And we're always working on new, and indeed recycling old. They're bringing back original working fluids like ammonia and water and carbon dioxide, etc. So it's a bit of fun as I age, but the enthusiasm's still there, We'll have a look at heat pumps for residential, commercial, industrial applications, and perhaps the supporting infrastructure which people can use either positively or negatively against it. The classic one I'm going to focus purely on electrical, vapor compression driven heat pumps. So electricity networks are always cited both as a concern and an opportunity, renewable energy being the opportunity. Wind and solar, etc., the concern being their capacity, and heat networks, something we in Northern Ireland haven't had a great experience yet with, but other places have used heat networks for hundreds of years. So it's one of these things that we can revisit and apply a lot of international best practice in our designs going forward, and it matches very nicely with geothermal. So a quick reminder about a heat pump. There's an air source one just to keep it simple, and I will flip back and forth between air source and ground source because air source are by far the more popular. But basically we take heat from an ambient source, ground, air, water, or whatever it is, and we transfer that hopefully into our home, our business, our process, typically using renewable electricity ultimately to get a very low carbon impact system. So how this works, very simply, is our working fluid, which I will call a refrigerant, is boiled. We'll stick with the domestic air source example for the moment, where outside air at a higher temperature than the temperature in the evaporator, or the refrigerant in the evaporator will boil. That vapor then is compressed to a higher pressure, but more importantly, higher temperature than the temperature required inside the house. That latent heat plus compressor work is then released into the home or into the building, and then you're left at 0.3 with a high temperature liquid, and we've got to expand that down to a low pressure, low temperature liquid, and we do that cheaply through a throttle valve, an expansion valve. We've researched using a turbine, which adds about 20% of the performance, which is a different, not mentioned today, but and background again. And that's what we do. So the working fluid is operating at a positive pressure, both in the evaporator and the condenser. The condenser is higher pressure, and this is why they're special fluids. Sometimes not so special. The fluids themselves, as I mentioned at the start, are changing. We are seeing the rebirth of the likes of CO2, which is R744 in my language of refrigeration, hydrocarbons. R32 is really not a hydrocarbon, but R290 is propane. HFOs and HCFOs are starting to get phased out, and I'll talk about that in a minute, even though they're currently quite popular. Ammonia and water. Ammonia is toxic, but an excellent refrigerant for industrial processes. Water is becoming very interesting as a high temperature refrigerant. And then the older ones, like 10 years ago, maybe more, we were using R410A. Now it's high GWP, global warming potential. It is also forever fluid. It gets into the water courses and stuff and stays there. So a lot of those fluids are getting phased out. And that's represented in perhaps a slide that also illustrates my longevity of career. When I started doing my PhD, we used CFCs. And that was the global, it wasn't global warming in those days. It was the ozone hole we were attacking. If you remember that catastrophe. So they were phased out for HCFCs, so hydrochlorofluorocarbons. The addition of the hydrogen molecule meant that they broke up in the atmosphere before getting way up into the high atmosphere and upsetting the ozone. They had an ozone depletion potential still low, so they were replaced with hydrofluorocarbons and then hydrofluoroolefins. But then the hydrofluoroolefins had a global warming potential, a greenhouse gas. And then they also discovered this lovely PFAS, the perfluoroalkanes, which means that they got into the water courses and forever chemicals and stuff like that. Because as a working refrigerant, we want a very stable fluid. You think of what it's doing, it's boiling, condensing, being compressed, being squeezed through a pinhole, around a cycle, millions of times in its lifetime. It has to be stable. The problem is that stability, when it gets out and gets into the atmosphere or gets into the water, means it stays there. So you'll see UK REACH, the drinking water initiative, or people, the PFA and stuff in Europe, EPA in the States, are all looking at alternative fluids now. That means maybe back to the future. So we're looking at propane, we're looking at carbon dioxide, we're looking at ammonia, etc. again, and other hydrocarbons. So it's interesting times, but it means that the industry is being responsible, in its terms of not only saving CO2 during the operation, but actually during any leakages or anything that was do happen, especially in transport refrigeration. There we go. Just briefly looking at where ground source and ground and water heat pumps fit alongside typically air source. As you can see, air source is by far, air to water, A2 water, monoblock, a complete heat pump in one unit, not split in any way, indoor and outdoor units, or anything like that. It's, the ground to water one is small by groundwater, or water ones are quite small in sales. And it's understandable why, when you see what's happening in the industry and in deployment. But we'll come back to that in a wee minute, because the impact of air source heat pumps have done a lot of work on. There's a publication we did where we looked at impact on a certain housing estate if we hypothetically fitted it out with air source heat pumps. You can see the electrical substations named down the circuitry and different circuits feeding different rows of houses in a social housing estate. So we put our money where our mouth is, and with the cooperation of the housing exec, we put in 8 heat pumps and thermal stores in similar social housing, in this case around Omagh, and as part of the Spire 2 project, which was Queen's, Strathclyde, ourselves, Dundalk IT, and a couple of industries sponsored by Interreg at the time. And let's say the housing executive for the rural-led energy transition, they put the gear in, we did all the monitoring and put some of the gear in as well, I think, too. And rather complex, busy graph, but basically what happens, imagine these 8 houses were in one street, side by side, and you start to look at them cumulatively, what the impacts would be. And you can see the 8 houses typically on a pretty cold period of winter were pulling about 20 kilowatts electricity. So what? That doesn't mean an awful lot. Some of you will have power showers that do more than that, but it's what we're trying to say is, if you have rows and rows of houses with heat pumps, there will be an impact on the electricity network, because the electricity network was not designed for this. It has capacity and it has abilities, but it's not designed for this. So there's a thing called after diversity maximum demand. And basically, there's assumptions made about the size of the wire in the street that feeds your house. And put it simply, on a cold night, there's no diversity. Everybody's heat pump will be on. So you have to look at this, in my opinion, even though I love heat pumps, you have to look at a cumulative effect and impact. So we took that back to our model. Sorry, before we took it back to the model, this is the UK study done by Catapult. There's 700, sorry, about 500, would be 700, about 520 heat pumps monitored across the UK. And you can see the air source ones are all between typically 2 to 3. A few odds and sods in there, which never got to the bottom of yet. They're a bit higher and a bit lower. And these are houses, house age band. And you can see it doesn't matter what age the house is. They're all operating about 2 to 3, which is, we can do a lot better than that. We'll come back to that. But that means our COPs that we were getting were slightly better. But, and we can make air source, ground source heat pumps better. But if you're going to pay about $7,000 for an air source and a lot more for a ground source, adding complexity to the cycle is maybe something that's going to be a hard sell. But we can improve the performance. We've done a few of these over the years. So the other way of improving the performance is using geothermal heat. This is a classic diagram produced by our colleagues in JS&I, DFE, etc., that it shows you the typical temperatures you might encounter. It'd be nice if we got some of the really hot ones, but we don't have that many spots for that. There's a few. I think Ballycastle can be hotter. And Antrim is in the 30s and 40s and things like that. And I'm assured that under Belfast here, there's about 15. So, it's a very, very useful sort of heat that an air source unit on a cold night can't access. And therefore, we get rid of this after diversity maximum demand problem, or certainly greatly reduce it. So, returning to our housing estate, and I just put a simple coefficient of performance of 4 in here, as opposed to 2.5, 3 that we're getting with an air source. And what we have on the black bar there is the substation's capacity. Well, the 7 substations on the streets they're named on. The air source in blue means that quite a few houses can't have a heat pump, or you need a bigger substation because the blue column exceeds the black capacity. But if you put a ground source in, you can see that you change that picture dramatically in that you're not gobbling up all the capacity of the local substations to run people's home heating, and ergo there won't be a challenge maybe if people also have electric cars, etc., except possibly on one street, and that's Ballygall in this case. So we are looking at reducing the challenge to our electricity infrastructure with geothermal heat pumps. And this is just shallow stuff. This isn't deep stuff around like that. Included in this, and this is just one of research throws in it, and current EPSRC project running, we're looking at how to integrate novel thermal storage in with heat pumps. And this is just a picture of our novel thermal store with its phase change material on board and its size against a domestic fridge, just to show that it fits under a counter. Should it ever get installed in a house. So a heat pump will be outside, whether geothermal or air source. And basically, this thing can, for example, if you needed showers, if that was just water, if that was a tank of water, it would do 2 or 3 people. This would do a family of about 12 people for showers. In other words, it'll heat the house as well. So it means that if the electricity supply, if there's too many heat pumps on, there's challenges, you've got a long period of time that you can run without the heat pump and you draw heat from the thermal store. So thermal storage and heat pumps go sort of hand in hand. Oh, so I have a very sensitive mouse these days. However, the downside of geothermal compared with air source heat pumps is sort of noted here. So you can see the quite big cost difference there is between an air source and a ground source. In the bottom column there, air to water is about 15,000, 9 to 15,000, and currently with a £7,000 grant in GB. Ground source, maybe 11.5 to 27, but the savings are huge, potentially up to. We'll show why it's up to in a moment. So the savings are really, really good because of that increase in performance. Just looked on the Energy Savings Trust website for Northern Ireland, and there's our fuel costs. If you were trying to put a heat pump in, admittedly it is a ground source. So I don't know the COPs and they've assumed for that, for this calculation, but oil is still cheap here. And if you have an brand new A-rated oil boiler, it is still cheaper to run. And you can see even an old G-rated boiler still is not really that expensive. So there is a job of work there for the policy people to do that, because we don't want to challenge fuel poverty. At the same time, anybody on the gas grid, we can make savings against, but against the oil is potentially not possible at this stage. So it's definitely a policy thing that addresses energy poverty for people, as well as trying to decarbonise. We know the cost difference. Air source was a box that sits out in a monoblock, what do you call a monoblock? So a heat pump and everything in one box sits out in your back garden. Fine. Some examples there of digging trenches for slinkies, for horizontal, for verticals, just diagrammatic of the spacing and the sort of typical things you would have. And if you get it wrong in the wee top box, you get frost heave and all sorts of stupidity happening. So it has to be done correctly, it has to be done right, but it is more expensive. So you start thinking about sharing loops now. You start thinking about, well, if we have our social houses that we did our testing are typically 5-6 kilowatts. So we could have maybe 3 of them at the bottom compared with one at sort of 30,000, it's 50,000 per 3. You could end up with about a 30% saving with sharing loops in small communities. And that's infant heat networks. That's the start of small community heat networks. And that's quite popular in rural parts of particularly Europe, etc. You can also improve the extraction loop for the verticals. There's standing water columns, there's closed loops, which is the standard sort of one, and open loops as well. That's why the diagram's not the best quality. But the standing water column does require a bit more specific geology to make sure it actually stays in the hole. And the closed loop is the classic. Open loop for aquifers does require permitting, I would imagine, because many of our aquifers do provide our drinking water and various other things. So it'll be quite important not to get that wrong. So, summarising what a heat pump has to do, we want the highest possible heat source temperature, and we want the lowest possible heat sink temperature. If we minimise what we call the temperature lift, we get a very high coefficient of performance. And that means we use as little electricity as possible. That's why there's that improvement in performance between ground source and air source heat pumps. So you can improve the building, underfloor heating, big radiators. You go to processes and industrial stuff, it's more process dependent, but there's always processes you can improve. Reducing the temperatures, have it more tighter, controlled, etc., etc. But the key message at this point of the talk is we're now electrifying space heating. So we are. And therefore, our major renewable energies are typically wind and solar. You couple that with thermal storage. When the wind blows, we load up our thermal storage. It doesn't matter if it's geothermal or air source. And when the wind's not blowing and you're relying on other sources, or maybe there's less ultimately less electricity available. You can draw heat from your store. And the store can be a tank of water, quite effective, can be bulky, ergo our experiments with phase change materials and things like that. So we can get these things to work quite well. But perhaps the holy grail for heat pumps and geothermal energy is heat networks. Unfortunately, Mother Nature didn't co-align our geothermal resources to where we live. So we will need heat networks. Now, whether we boost the heat at the source end and deliver it to the town, or what I think is more sensible is deliver the heat from the geothermal, which will be a lower temperature and therefore less heat loss, to where we need, and then you boost it at the target, is probably the way to go. So there's all this stuff about one to fifth generation of heat networks. Ultimately, a fifth generation is bi-directional. It can do cooling, do heating, and capture waste heat. It can scavenge. It can do whatever you want it to do. Whereas the first generation steel pipework type concepts was a big fossil fuel boiler or power station and heat. Was that it? That doesn't negate a first generation one. If you have high temperature waste heat or high temperature geothermal heat, the only bit challenge you have is you're maybe going to go to steel piping. I think the plastic piping's limited to about 80 or 90 degrees. So it's a horse for a course in this case. Just because it's fifth generation, it doesn't mean it's the be all and end all, but it does mean that it's more flexible. More people can make use of heat networks, where you can see seasonal storage, space heating, space cooling, data centers with waste heat coming in, swimming pools being heated, commercial buildings, industry processes, drawing and giving to a heat network. And it takes use of what you can get and how you can use it. And a heat pump is key to that for both ways, because a heat pump can be reversible. Just because my opening diagram showed taking heat at the bottom and bringing it out the top. You can take in heat at the top and put it at the bottom if you want. You just reverse it. Don't reverse the compressor, the fancy little valve you have to use. But you can do that, and ergo the system runs, and ergo you can provide cooling in the building, and that waste heat is then stored. And we've seen some potential examples of long-term seasonal storage and geothermal stuff in aquifers, in pits, etc., in the ground even, where excess summer heat is stored for winter usage. And indeed, one of our EU projects many years ago, still running as far as I know, we built a heat pump to utilise a solar thermal array and 800 tons of water. So the solar thermal array heated the 800 tons of water in a Polish hospital, and that heated the building until it no longer was high enough temperature to provide sufficient heat through the existing radiators of the building. And then the heat pump kicked in and boosted from the 800 tons of water, boosted it to the radiator temperature required. And we were getting COPs of 6 and 7 sort of thing on that. It was quite good as a project. So there's a lot of learnings that can apply to geothermal alongside thermal storage. Somebody may have seen it on the tour if you were over with us last year. There's one of our current heat pumps. It's a slightly older picture, it's changed a wee bit since then. New kit added to it since then. But it results at that time where if we had sort of 40-degree heat coming in, we could get a COP of about 6, 7, for lifting a couple of, 20, 30 degrees. And if you lifted a bit more, obviously you dropped a bit more. But you could get up to a COP of near 9. So data centers, waste heat coming off, etc., etc. You can harvest those and boost them to what we need. The bigger the lift, the lower the coefficient of performance. But as long as you get a sufficient coefficient performance for the economics, this can work. And part of the IEA, International Energy Agency Annex, Heat Pump Technology Annex, called 60, it's looking at retrofitting to large commercial buildings, moving up a scale in building. And there's the partner results for, it's Canada, US, UK, quite a few European countries, looking at large commercial buildings that have been retrofitted with heat pumps and what the types would be. Unfortunately, there's only a couple of ground ones, 13% and 4%, monovalent and bivalent. So either just heating only or heating and cooling. So they're not common enough yet, and maybe it goes back to the earlier arguments of the capital cost. Simon Todd did a lovely study there recently on an IKEA building that has a lovely ground source heat pumps. I'm not stealing any of Simon's thunder by using that case study, but it's it's Causeway Geothermal. They did a very nice study on an IKEA building, which is a heat pump, providing the heating. So it's through boreholes and things like that. So it does work and can be. We know it works. It's just the air source has got in first because of economics, and also sometimes in like the VRF, systems and a few other things, they are probably easier suited to that type of building system as well, but not impossible. Getting to the point where you start to think about industrial heat pumps, then I probably showed this slide before to some of you at the talk last year, but there's a lot of products now starting to appear in that 100 to 200 degrees C process range. UHT milk is about 166 degrees. So a lot of the dairy industry, etc., can make use of heat pumps that now exist quite happily. So there's, as you can see, there's a huge part that we're not really addressing yet. And, there's some ideas on that too. But it's something that we really need to try and decarbonize and think about how we're going to get rid of. Heat pumps are getting into domestic big scale. They're starting to creep into commercial because, again, it's buildings, it's still the same temperatures, just a bigger unit. But when you start getting into the industrial stuff, there's not too many options. The next slide, you think there's a lot of options, but there's not that many. I think the record claimed is just about 300 from Man's Energy Systems system. I think it'll do about 300. The water-based ones, the highest ones are in the 200s for mechanical vapor recompression, i.e. putting steam into a process. Our current proposal, which is being worked up, will look at about 320, but that's probably the upper limit of water as a refrigerant. That takes us up into that brown zone there, which is about 11%. But we've still got this big red zone up here, about 50% of process heating demand that's technically out of our reach at the moment. So what's within our reach, as you can see, the temperatures, they say, since this graph was done, there is a claim that somebody can get to near 300. But there's the different stuff from Annex 58, which is the high temperature heat pump annex. And you can see a list of manufacturers there, some of which will be familiar to you and some of which will be new. But these are ranges and capacities. And here in Northern Ireland, the capacity is a bit of a challenging part for us because some of the high temperature process we need, nobody builds a heat pump that's small enough for that. We're talking typically 5 megawatts being some of the smaller ones, 10 being one of the more industrial standard ones, and we don't have too many processes like that. And likewise in Ireland, probably the same big chunks of the UK. So there is a market for smaller scale, high temperature stuff, for those that do the food processing up to about 200 degrees, etc., plus a range of other things. And those are just samples of the people or the companies that develop equipment noted by that annex, which is finished last year. This is an interesting chart for the point of view of where we're at with things. So if temperature lift along the bottom against COP, if you have a low lift application, you get a very high COP. So if you've got nice geothermal at 40 coming out of the ground, and you want to bring it up to 60 for space heating, you get, or should get, a very high coefficient of performance, a correctly designed system. However, for process heating, when you're looking at up to 200 degrees, the lift maybe of 140, 150, 160 degrees lift, you really are on the realms of a COP of under 2. So this is where the cost of electricity comes into it and what the economics of this would be. And these are, as you can see, heat pumps. These are vapor compressions or mechanical vapor recompression. Turbine producing steam. So they are just pushing steam out, so, so they're quite special animals in a way. But there's not too many of them either, unfortunately. Quite a few reds. But it's a challenge for us to think about decarbonizing higher temperature heat processes because we're at the limits nearly of what this can do. Was a vapor compression cycle with a evaporator, a compressor, a condenser, and an expansion device. Yes, I can put a turbine in because we've got a high temperature difference and recover energy. I get about 20-25% back on a turbine. I've done that successfully. So you can take advantage of certain things, but then you're adding capital cost all the time. And you're competing effectively with a boiler, which is basically a flame inside a box, surrounded by, on the outside of the box is water inside another box, or outside another box, inside another box. So you're competing with a well-established, relatively low-tech technology versus what is something that can be quite complex. And in our ever-increasing pursuit of performance improvement, it becomes more complex. So that huge opportunity is not out of reach, but needs a different thought. And I forgot to put the reference on this one, but we're working on gas cycle. So instead of condensation and evaporation, it's all gas. The Brayton cycle, reverse Brayton cycle. They give it to anybody who likes their thermodynamics. I do. I'm sorry about that. But 500 degrees, COP of about 2.8. 1,000 degrees is possible. Now, the background to this is materials. So my models are fine, but the models currently don't deal with the materials. They only deal with the thermodynamics. So the materials that can cope with these sort of temperatures, you're looking at jet engine technology, you're looking at specialist metals, etc. But maybe with a fair wind and a decent proposal, we'll get a crack at this. Might not tell the university because we're sitting there with a 500 degree C heat pump in a lab. Fahrenheit 451 is the combustion of paper. So, anybody remembers their science fiction? So, to conclude, you see a lot of myths about heat pumps. Noisy. Air source units do emit a noise, but ground source are quiet. Can only be installed in new builds. Been running a heat pump in my own house, which is 1970s for years. Radiators don't warm up. Need to be the right size, and they take longer. But even an air source heat pump in a cold morning, there's a big cold bit of metal sitting out in your back garden, and it's going to take a wee while to warm up. You turn it on a bit earlier. Can't run on solar is totally mythless. Solar, people that have heat pumps have put in PV, love it. Don't provide cooling? Yes, they do, reverse the cycle, but you have to design and have that. They don't last long, 15 years plus, same as a boiler, but there's higher capital cost. Can last 20. But finally, hot off the press, just a couple of days ago, Ed Miliband announced the UK's modern industrial strategy on clean energy industries. And heat pumps is a whole chapter to itself. 5 billion gross value added industry, ultimately. Yes, they focused on domestic, but there's commercial buildings, there's industrial processes, which maybe will be obviously less than the domestic. But it is a huge potential industry that they're hopefully going to support. And for us in geothermal, that must be a win-win. Thank you very much.